question. Is the microphone working and everything?
Microphone is, but now I don't know. I don't see the slides anymore.
No?
No. He just fixed it.
His fix is broken again? Oh.
Yeah. So 5 minutes ago I could see them. So I don't know what he did in between.
I don't think he's touched it.
Okay.
Maybe, I don't know. Yeah, you can ask him. Maybe use a different laptop. So it's all set. I don't need to press any buttons anymore.
For the mic. So you see it.
Okay, perfect. Thank you.
No, I'm just asking. 1 minute. Yeah, either HDMI or USB-C. And then a USB-B. I think, no, these are B or A.
Oh, for the kicker.
Yeah.
Yeah.
There you go.
I don't really plug it in yet. Don't want to really do it outside.
No, but you can put it on the first line.
I heard there was some additional errors. Why does it? Here, and then we.
No, BJ said that we should all, for the questions, we should all stand here. For the questions, yeah, I think it makes
I don't know how to choose best people. I mean, I know basically what everyone has done.
That's basically what you need to do. Like, whoever. And it's also going to look a bit weird if you change halfway. So. Just checking that everything is more or less. There's a lot of hidden slides. I don't know why now. Like I don't think that yesterday there was that many hidden slides.
I think you know this better, Casper. That's why I don't want to do it.
For the questions, you mean?
They actually want me to make
I want you to do it as well. I'd prefer you do it.
Carlos, will you lead the questions? Just do what
Goedemorgen en welkom aan de faculteit der Lucht- en Ruimtevaart. I will continue in English. My name is Marilena Pavel and I'm going to chair this morning's session. We have an exciting day today, so our students will present their final design synthesis exercise. And we have the first group, which is let's see. Oh my God. A presentation on a sustainable family. Do we have the jury members in this room? 2? 3. Okay. So that should be okay. The presentation will go as follows. The students will have a presentation about 20-25 minutes. And then there is a possibility of answering questions from the committees, but also from the parents and family. About 10 minutes. And afterwards, there will be a ceremony of handing in the diploma. I have them all here. So the tutor of this group will hand in the diplomas. So I give the mic to you, and success.
Thank you very much. Okay, welcome everybody to this presentation for this aerospace project. As you will have probably noticed by now, it is very, very warm at the moment. And this has been a trend for a number of years already due to this unfortunate thing we call global warming. Now, aviation is also a contributor to this, and there have already been multiple projects which have aimed to provide more sustainable alternatives to help alleviate this. For example, there's a few electric aircraft like the Viridian and the Aviation Alice, and a few larger ones as well, such as the Hart ES30 and the Elysian. And there's even an Airbus hydrogen concept, the 0E. However, there's one thing that all these aircraft have in common, and that is that they are single aircraft designs. Now, if you know a little bit about the commercial aviation sector, you'll probably know that most of the commercial aircraft are not single designs, but are actually part of larger families. Take, for example, the A320 family. It has 4 different versions with different lengths, which can offer different passenger configurations. They also offer different engine options to give airlines more operational flexibility. Now, we have also done this. We haven't designed a single aircraft, but an aircraft family. This way, we hope to address the emissions within the regional aircraft market, and by offering airlines multiple different variants they can use, we give them more operational flexibility and allow them to reduce their maintenance costs, which means, and this way, we hope we can actually implement a commercially feasible project which can make a meaningful difference to climate change. We will be presenting by starting off a little bit about the configuration of our aircraft, start off goals and then the configuration of our aircraft. Next, we'll go into the design process. After that, we'll have a look at the outcomes of all the research that we've done, and finally, we'll draw our conclusions. But before that, I want to give you a little bit of extra context. As I already mentioned, global emissions are a major problem. As it stands, the aviation market contributes about 4% to global warming. However, it has shown to be one of the most difficult sectors to decarbonize due to the technological and economical challenges involved with doing so. And worse yet, it is expected that the contribution of aviation is going to significantly increase over the next few decades, as is shown by the blue trend prediction here. This means that if we want to achieve the goals, the targets we have set out for ourselves to reduce climate change, as shown here, we need to start making a difference now. And with that challenge in mind, we set the goals for our project. First of all, we set a number of emission goals. We aim to reduce the CO2 output by 80%, nitrous oxide emissions by 30%, and the emissions of non-volatile particulate matter by 30% as well. In addition to this, we've set a number of goals for the operation of our aircraft to ensure that it is commercially feasible. Here, we aim for an entry into service by 2045, a commonality between the family members of at least 65%, and we hope to have a cost per available seat kilometer that is at most 15% more than current alternatives to make sure we are competitive in the market. We also looked at a few other additional goals, such as on turnaround time, to make sure smooth operation can be performed. With these goals in mind, we looked at the configuration. Initially, we analyzed 3 different aircraft concepts. First of all, there was a laminar wing, which you see on the left. Then the lifting fuselage with a fully hydrogen-powered turboprop shown in the middle here. And lastly, there was the strut-braced wing concept. It was found that both the lifting fuselage and strut-braced wing concept performed very well, and by combining elements of these 2 concepts, we came to our final design. Here, we use a strut-braced wing configuration. This means that there is a structural element which connects the bottom of the fuselage with the midpoint of the wing. This allows us to alleviate the loads in the wing and achieve a higher aspect ratio. And thus, it allows us to improve the aerodynamic efficiency of the aircraft. This is paired with a fully liquid hydrogen turboprop. This way, we can limit both the emissions and the risk involved with the project. With this configuration in mind, we can look at the family. There is 2 different passenger configurations. First of all, there is a larger passenger variant, Leaf A, which is capable of carrying 84 passengers over a range of 1,500 kilometers. And then secondly, we have Leaf B, which is a slightly smaller variant with 58 passenger capacity and a range of 1,300 kilometers. On top of that, we also did a conceptual design of a possible cargo variant, Leaf F. With this configuration and family in mind, we went more into detail in the design process, which Casper will tell you more about.
All right, thank you, Sean, for presenting the concept trade-off and its outcome, the final design. Now we can build on that result by explaining how sizing of a strap-braced family of the regional aircraft was performed. Aircraft sizing process is iterative, meaning that the subsystems are mutually interdependent, and change in one of them automatically requires a change in the other. To facilitate that, we developed an iterative Python algorithm that built on the empirical equations adjusted for the use of novel technologies, such as the liquid hydrogen and the addition of the strut supporting the wing. We started off with initializing the weight of the aircraft. That was used to update the matching diagram to find the wing loading and the power to weight ratio required at the design point that we have chosen for our design. That helped us to better define the shape of the wing and the size of the engine. Then we followed with the location of the CG and empennage sizing to make sure that the aircraft is stable and controllable. That allowed us to calculate the new mass of the aircraft, and so the iterative cycle continued. The iteration runs until the difference in the final values between the aircraft design parameters is above a certain specified number, and once it goes below, the iteration loop stops, revealing the final design. Since the task was to develop an aircraft family, some changes had to be made to make sure the high commonality index between all of the aircraft could be achieved. The code, for example, designs all aircraft with the same vertical tail, which is sized for the more constraining variant. So once the aircraft vertical tail was sized, we could play with the value of the tail length to make sure that both aircraft stayed stable and controllable. Iteration loop converged in 13 iterations, with all of the values gradually approaching the final design values, as can be seen here with the evolution of the maximum takeoff mass. Our code allows us to create a family with a high index of same parts, reaching 76%, by keeping the same nose, middle section, tail, empennage, engine, as well as the main landing gear. Let me provide you with outline of the main parameters that was given to us by the Python sizing algorithm. We have the maximum takeoff mass, empty operational mass, total length of the aircraft, and fuel mass. Here an interesting observation can be made, which is that the Leaf B variant, which is the shorter of the two, is 14% shorter than the Leaf A, but only 11% lighter. And that result can be explained by the fact that both aircraft, from the structural point of view, differ by addition or subtraction of the straight fuselage sections. And these have a lower mass per unit length than other sections, such as the intersection between the wing and the fuselage. Now we can move on to the subsystem design. When looking at the aircraft from the outside, all what we can see is the outline of its shape. To better understand the subsystem design, though, we have to dive one level deeper, revealing the internal structure of the aircraft. Here you can see that for the fuselage, frames and stringers were modeled, spanning all the way from the front of the aircraft, where the random is located, to the back, where the APU is housed. For the wing, we modeled the spars and ribs as the internal structure. Also, one can notice the liquid hydrogen tank located in the back of the cabin, nicely incorporated into the fuselage. The story about the subsystem sizing will be discussed for each of the subsystems separately, starting with the internal structure of the wing. Here, the backbone is composed out of two I-beam-shaped spars and 25 equidistant ribs positioned across the span of the wing. Two extra ribs were added to provide support at the connection point between the wing and the strut, and to transfer the shear loads from the wing into the fuselage by the mean of the strut. Strut is a symmetrical airfoil with a chord of 23 centimeters. It should be noted that for both variants, the same wing is kept. Information about the internal structure of the wing, together with the maximum takeoff mass calculated in the sizing algorithm, allowed us to predict the deflections and internal loading within the wing. Here, the beneficial effect of the strut can be easily noted. The bending moment inside the wing was drastically reduced, providing a bending relief at the wing root of significant value, as well as significantly decreasing the tip deflection between the supported and unsupported wing for both of the aircraft. As for the internal fuel tank, all of the fuel is stored in a single, non-integral fuel tank in the rear section of the fuselage. Since hydrogen is stored in a liquid form, it requires cryogenic temperatures of negative 250 degrees Celsius or 20 degrees Kelvin. Throughout the mission, the fuel warms up, requiring us to install a thick layer of isolation. For both of the tanks, for both of the variants, same hydrogen tank is used, filled up for different levels to better tailor for the mission profiles that the aircraft were designed to. The total usable volume is 14 meters cubed, and we can store up to just below 1 ton of liquid hydrogen inside the tank. As you can see, the tank is not fully filled, giving us a little space for the extra range if the operator decides to deploy the aircraft on longer missions. It should be noted here that the Leaf B variant is the more constraining when it comes to the liquid hydrogen tank sizing, as the average density of the fuel inside is lower, and that causes the pressure rise inside the tank to occur faster. Now we can move on to the propulsion subsystem. We selected 2 turboprops to power our aircraft, and the turboprop engine is arranged in a twin spool configuration. It powers a constant speed propeller, and its mass was estimated to be 820 kilograms. We can look at the propulsion system chart, where the 2 spools can be visible in the white, connecting the low and high pressure components. It should be also mentioned here that to increase the efficiency of the engine, heat exchange at the exhaust was was incorporated to preheat the liquid hydrogen from those cryogenic temperatures before its injection into the combustion chamber of the aircraft. As for the propeller, we've chosen a 6-blade design with a diameter of 4.05 meters. And as I mentioned before, the propeller spins at a constant rate. Finally, we can touch upon the design of the landing gear. We've chosen a common tricycle configuration with each of the landing gear bogies having 2 wheels attached to it. The landing gear is retractable since aircraft is cruising at a speed of 0.62 Mach. I can also say that the front landing gear is fully enclosed within the fuselage structure, whereas the rear landing gear is air open, meaning that the wheels are in contact with the flow air once retracted. And that concludes my section about the detailed design, and now I will pass on the floor to Marius, who will talk to you about the sustainability.
Thank you very much, Casper, for discussing the final design. I'll now proceed to the sustainability aspect of this aircraft, which is, of course, the reason why we are presenting today. Now, we have set ourselves goals presented to you by Sean earlier with respect to carbon dioxide, nitrous oxides, and non-volatile particulate matter. And as we can see on the screen, these goals are always achieved for both variants Leaf A and Leaf B. It is noteworthy here that, for example, the nitrous oxide emissions are drastically decreased, especially from cruise phase, but also because of lower fuel mass flows relative to conventional kerosene aircraft, despite the higher emissions index of NOx of hydrogen combustion. Furthermore, we can also observe that non-volatile particulate matter is nearly at 100% reduction because hydrogen combustion emits a negligible amount of this. That being said, hydrogen is a complicated issue. There are a significant amount of technical challenges and operational challenges that need to be addressed. For instance, the hydrogen has to be produced from somewhere, and currently hydrogen is produced from fossil fuels predominantly, which completely defeats the purpose of a hydrogen aircraft. That means we have to establish hydrogen production infrastructure and on-site distribution infrastructure that doesn't compete with existing hydrogen and electricity demand. We consider that hydrogen production through electrolysis is the greenest solution of them all. Furthermore, aircraft have been flying on kerosene and petrol for 120 years, this entire lifetime. So there do not exist any maintenance procedures, certification procedures, certification standards, or operations procedures for hydrogen. And all of this needs to be developed before the entry into service of 2045. This is a significant challenge that we cannot understate, but we believe that it is fully feasible before the entry into service. We ask ourselves as well, where does this aircraft fly? Now, we have also established earlier that this aircraft is meant to fly between the 1,500 and 1,300 kilometer range. And from Amsterdam Schiphol, that reaches most of the economic hubs in Europe. Turboprops are typically used on low-density traffic routes or high-frequency routes on, of course, the regional and short-haul flights. And ATR forecasts, ATR is the leading manufacturer of turboprop aircraft, that about 2,100 extra turboprops by 2045. So, of course, later on that increases the amount of turboprops flying in the air by a significant amount even further, which leaves an interesting value proposition for our aircraft and an existing market. Now, you have noticed that we have discussed only 2 of the aircraft, Leaf A and Leaf B. That leaves the Leaf Freighter, or Leaf F, to be discussed. Indeed, it will be a Leaf A modified, where we remove the furnishings and reduce the amount of cabin crew on board to achieve payloads of a mass of more than 10 tons. In comparison, the ATR-72 turboprop reference aircraft freighter version has a payload mass of 9.2 tons. And we achieve this by a similar total cargo volume. This would also unlock a lot of possibilities for sustainable cargo flight, And of course, being the family advantage, we do not have to design a whole new clean sheet aircraft just for cargo operations, significantly reducing design cost and ultimately economic cost for customers. As discussed earlier, hydrogen is a novel fuel, and so hydrogen has unique challenges for turnaround time at the airport. The main challenge is that you cannot refuel, that currently we do not deem it safe to refuel at the same time as we perform cargo and passenger operations. So indeed, first we have to establish passenger operations, we have to deplane the aircraft, and then we can refuel before boarding passengers again, and then taking off ultimately. We have set requirements on turnaround time, as was mentioned by Sean, of 60 minutes, and for the aircraft that we have, we had established that Leaf A would have a turnaround time of 58 minutes, including margins of the safety weights and variance in passenger and cargo unloading, which meets our expectation of 60 minutes. Hence, the turnaround time requirements are met, our goals are met. Now, of course, in this world, things do not happen when cost is a problem. We performed a statistical analysis on the operating costs of this aircraft and actually deemed it, based on economic incentives and fair carbon pricing, that Leaf A would be actually cheaper to operate than the ATR 72 flying in 2045. Leaf B is actually slightly more expensive, but still below the 15% extra limit that was mentioned to you earlier, which deems that this aircraft is still economically viable, especially when considering extensive investment in hydrogen infrastructure. When assuming a revenue of 46 million euros per aircraft, we deem that it is possible to also, as a manufacturer, generate profit out of this. We computed a break-even market share of 17%. That means that the costs of producing the aircraft relative to the fixed and variable costs would match out in this case of 17% when considered with the 3,000 or 3,500 so aircraft flying in 2045. Based on the assumption of a 20% market share, we established that we get a return on investment of about 5%. And so we have established that revenue exceeds cost, and so we have profit. Now we can look forward to the project future. We have produced a preliminary design for the Leaf family. That being said, of course, the subsystems need to be designed. We need to produce prototypes. We need to validate these prototypes. We need to test these prototypes. For an entry into service of 2045, we deem that 2037 is an acceptable year for this to happen. Secondary, we need to fly these prototypes. We need to certify them. We need to show that they actually are safe to operate. And of course, we need to produce them and start mass producing them until, while customer orders exist. And we hope to do that until 2054 or so, when we can also consider even making some new engine options, possibly incorporating open fan technology or improved combustion thermodynamics. We hope to support this aircraft until 2100, where we provide maintenance support and operations improvements over this lifespan until this year, as you can see on the screen. And so now we can recap the family benefits. We start with a design time reduction. The aircraft is just merely the aircrafts are merely stretched or condensed versions of each other. That significantly improves design time and engineering effort. Second, flight operations are simplified. Crew members are shared between, crew members can operate an aircraft and another in the exact same cockpit. And furthermore, maintenance procedures are simplified. Ground mechanics can use the same tool set. They use the same repair parts. They merely need to use them and maybe a different amount of time between the aircraft, delivering a significant advantage to the family concept. And we do this all to reach our destination of sustainability. An aircraft is nice when it is single, but it is always better to fly with siblings. Thank you very much for listening.
We are going to have some questions. May I ask the first question?
2045.
2045. 45, okay. Do you have a risk analysis? What do you think of the risk of introducing this into the market?
Yeah, so we do have some risk analysis that we did. Sorry, the question was if we had any risk maps or if we had done any risk analysis based on this timeline. We have, so I'll leave it to Lisa to explain that.
Thank you. With incorporating liquid hydrogen in 2045, there are some risks that come with it. For example, certification is quite a risk because hydrogen is very combustible. So when it comes into contact, it can explode. But we believe that by going through a long certification time, as was shown in the presentation as well, we can get the aircraft certified. Also, we introduced a lot of contingency. So, for example, in the tail cone where the hydrogen is stored, we have some extra space below to allow for some safety materials, such that whether some kind of crash or tail strike happens, that the hydrogen is safe.
Okay, thank you very much.
Thank you, Lisa.
I have several questions. One is, you are very much dependent of the rest of the world. Is there an engine? Is there a hydrogen infrastructure? You will not make it. You will just make the structural part, the aircraft. If that shifts, if the engine is not there, if the infrastructure is not there, what do you do? When do you stop investing your money?
So the question is that there has to be quite a bit of infrastructure and also components for our aircraft that maybe we don't necessarily are planning on manufacturing. And so I think I'll leave this question to Lindsay, as she did some of the operations.
Yeah, so thank you. So the operational part of this, we really have to make sure that we have good contact with, for example, EASA or the FAA, depending on where we're going to fly, to make sure that the certification and all that stuff happens, as well as stay in direct contact with airports that we're planning to fly to make sure that they have, for example, liquid hydrogen refueling options, because that is obviously a necessity for our aircraft. And with this, we do expect that we would be able to fly in 2045 as planned.
But is that availability on that risk map?
Can I take?
It is a risk.
Yeah, I'll give it to Marius.
Now we do accept, indeed, it is very risky to invest in hydrogen infrastructure. Indeed, that is also why Airbus ultimately delayed their Zero-E program, because they didn't see a widespread investment. And we do acknowledge that indeed, this program eventually would have to be cancelled should there not be enough government incentives, economic incentives for it to happen. With regards to a specific date when this would happen, we did not consider that. But this would happen very quickly in the subsystems design or prototype manufacturing if we cannot deliver certain key performance indicators, if that helps.
And sorry, just one last thing to finish answering your question. But it is something we have considered in the risk maps. Well, it's that here we can't show like. Yeah, we don't fully have the exactly what each number means right now, but it is something we considered, and we did add some mitigation strategies. Also, if say some of your suppliers are delayed with the development of this technology, how can you solve those issues? So it is something we have taken into account.
Next question, please.
Yes, thank you for the nice presentation. I like that you showed all the processes that you went through. You mentioned some disadvantages of non-family of aircraft. Can you also think of disadvantages of a family of aircraft?
Okay, well, the question is if we have mentioned a bunch of advantages of having family members, but what are the, say, the negative aspects of having a family configuration? So I'll leave that to Sean.
Yes, thank you. Thank you for the question. So the main disadvantage is that each family member will have slight weight penalties. When we need to design it, every component that we want to be common between the aircraft needs to be designed to comply with both aircraft. And for some subsystems, especially things like the landing gear and the wing, This means that for the variance, sometimes you have a slight weight penalty due to the constraint that you add due to that family aspect. And this can slightly decrease the fuel consumption and slightly increase prices. But generally, it decreases the overall cost of the program due to the fact you don't need to design separate aircraft.
One more question. I want to look into the design. Of course, the goal is to get a reduction of 8% carbon footprint. So what was the basis of your design? Was it the engine? And from there on you went to the airframe because you started with the airframe, but it's the engine who's reducing carbon footprint, all the footprints. And so in very simple military words, when we reduce in emission, we lose power. So can you elaborate on how your steps exactly were? And what I missed was materials.
Okay.
Can you elaborate on that?
So if you want to go to the slide on the trade-off at the start, or if you have one of those. So the question was mainly what our design process was and what trade-offs necessarily we had to leave behind to be able to to design our aircraft. So although I'll lead the question through in a second, I would like to say first we started with these three firstly with these three designs, and then we performed a trade-off on them. But even after performing the trade-off, we still found that some technologies from some of the one of the designs was better with some of the technologies from the other design. So we merged those two, and then we went on the basis of first selecting the kind of wing, in our case a truss-based wing, and then we really designed around that. So we then developed, we had chosen a turboprop, and then we developed some of the technologies around there. But I will lead the question to Marius, which he worked a bit on class 2 weight estimation as well, so he can also help with that.
Yeah, indeed. Hydrogen, the key advantage is of course hydrogen for the emissions, but of course the strut-braced wing also delivers quite a bit of efficiency improvements. Studies have shown that it's maybe because of the extended aspect ratio that can be achieved from the strut-braced, we can also reduce fuel burn by 20% or so, which further helps into reducing the overall hydrogen consumption. And of course, novel aircraft materials were also studied to achieve lighter airframes. If you would like more information, I can pass to my colleagues as well on that.
So for the fuselages, we chose aluminum lithium alloy that gave the lighter structure. And for the frames, we chose an aluminum alloy that was also cheap and light. Did I answer your question?
Yes. Thank you.
Some other questions? Yes, please.
Showed a very nice graph of thank you for the presentation. Vertically, it was very nice. I enjoyed it. My question is actually about the turnaround time. When you're refueling the aircraft, with the tank being all the way in the back, how far is there any possibility of it actually tipping backwards when the fuel tank is filled and you start boarding at the back?
Yeah, so the question is if there's any effect on the CG mainly, and if that can lead to a tip over when the fuel tank might be empty or when it's being loaded with passengers. So I think I'll lead that question down to
Would you
Lindsay,
like to answer?
or to Lisa, and they can.
Yes, actually during the class 2 sizing, we have made a loading diagram. So that starts with the empty operational mass, and that has a certain center of gravity location. And then after that, you go through all possible boarding possibilities. And that leads to a graph that gets the outermost CG positions. And with that analysis, we found that there's no possibility of tip back, also with the fuel creating quite an aft excursion. But that wasn't really a problem for us, also because liquid hydrogen is a very light fuel. So the excursion was a few meters, but not very significant when you compare it also to passenger loading. Does that answer your question? Okay, thank you.
You said you chose a truss-braced wing design because, of course, these are usually for higher aspect ratio wings. Did you consider the effects of aeroelasticity not only on the wings but on the
On the what, sorry? Can
On
you?
the trusses.
Okay, so the question is if we consider the effects of aeroelasticity on the truss as well as on the wing. So I'll give that question to Casper.
Thank you so much for that question. To address it, we've simulated the vertical deflections of the wing, how it deforms as a result of the lift force transferring into the bending moment. For the strut, it is simulated as a single force member, which means that it only carries axial loads when in flight and a bit of compressive loads when on the ground. So for that, it can only deform, either elongate or contract. We've checked some equations for the column buckling, and we concluded that for the geometry of the truss that we have chosen, no column buckling will occur. Does that answer your question? Yeah. So as I said, the strut is only a single force member. I'm sorry? Flutter of the structure, that was not considered. Thank you so much.
So the question is, we use a lot of empirical methods, and those are based usually on statistics. And the question is more like what modifications did we do to those procedures to make them adapt to this new hydrogen aircraft? I'll leave that to Marius to respond.
Yeah. So indeed, the extra the interesting parts here would be the wing geometry that actually computes an extra strut inside the mass, but also we have the fuel estimates as well as mass estimates that come from the tank sizing, which significantly increases the aircraft's mass and both scaling the fuel and the fuel and the tank at the same time, whereas conventional aircraft, we'd consider that the wing can carry a good amount of the fuel without a significant extra mass. Yes, that would be the novel technologies in there. Also, the turboprop combustion has some particular.
Yeah, so the turboprop combusts the hydrogen. For the engine itself, we analyzed we based our a bit on some literature on existing hydrogen research. However, specifically for the hydrogen tank is also where we made big changes. This is of course very different from a conventional aircraft where you have a fuel tank in the wing. So instead of doing an analysis for the fuel tank in the wing, we did a separate, more detailed analysis of the hydrogen tank where we integrated pressure over the flight time to find what the weight of the tank is. I don't know if that answers your question. If Lisa can go into more detail about the tank if you want, but if that answers your question, we can get. Yes, so the question was what the gravimetric index of a hydrogen tank was, and I'll give that to Lisa to answer.
We ended up with a gravimetric index of 0.39.
That would depend, of course, on the definition of gravimetric index, though.
Yeah. Yeah, we divided the tank mass divided by the maximum fuel mass loaded. Okay. Thank you.
Very short question. The very last one is on this subject. Did you consider the mass of the fuel to be at the center of the tank, or did you consider the fact that when your aircraft is moving, the hydrogen will move in the tank?
Yeah, so the question is,
Sloshing.
Yeah, the question is if we considered sloshing. I'll leave it to Lisa to also answer that.
Very short. Yeah. Oh, well, for now we have not considered. For now we have not considered sloshing, but we did keep some extra space in the fuel tank as well. As you've seen, we have more space in the fuel tank that is needed for the missions, because we do want to, in the future, incorporate some anti-sloshing materials or designs. But right now that was beyond the scope of our design. Okay. Thank you very much.
Okay.
Give them to each of them, yes.
Okay, some extra steps
say
too.
2 or 3 words.
Of course.
I don't know if
You
need
can,
Yeah.
yes, you
I'll
can
take it.
take that one.
Yeah. Sorry, just setting some things up here.
Should we maybe?
Shall we move down in front of the stage?
Maybe it's easier.
That's also nice if you would like that.
Yeah, I think it's better. It's a bit tighter.
Just come in front. We'll figure it out, or somewhere. So that everyone can see you and you can take some pictures. So good morning, everyone. Thank you all for being here. It's nice to have such a full lecture room. That's actually, I have more people here than during my normal lecture, so it's actually very nice to see. My name is Peter Jan. I'm the assistant professor here at the faculty, and during the last 10 weeks, I was one of the supervisors of this amazing team, together with Federico and Dierensch. Thank you a lot also for the collaboration. So also I would like to say a couple of words. I'll keep it brief. But first of all, I really enjoyed working with you as a group. All of you were very committed to this project from the start. You went through a lot of technical decisions already in the beginning, but you somehow managed very well, I think. And also, I think this outcome is something to be actually very proud of. Also in research, we don't know yet how to handle this family concept for this novel energy carrier, so I think you really also added or answered some of the research questions there. So thank you for that. But besides this technical work, I also want to mention that actually this group, what they were really good at was striking a balance between being very professional, but also having fun. So I think all your meetings, the review meetings were well prepared, a very professional way of answering questions. But then when I visited the group, they were also joking, and actually unofficially maybe we also had a noise complaint from a different group, but I cannot confirm or deny that. But so what I want to say is it was a pleasure working with you, and very well done. So I think then we'll continue with handing out the diplomas. So first of all, can I ask Lindsay to come to the stage? Congratulations. Well done. Or maybe you also get a nice folder. Maybe I'll ask you to keep it very safe in there. Then, can I ask Sean to come forward? There you go. Congratulations. Well done. Also a little folder. Then I think it's time for Marius. Very well done.
Thank you.
Oh,
thank you so much.
No problem. And also binder or folder for you. Then the next one, Casper. Here you go. Very well done. Oh, sorry. Let's do it like that. I'm not sure. And a binder for you.
Excellent.
And we have Carlos. There you go. Very well done. Oh, sorry, Carlos. Extra empty present. Okay, next one. Dan. Oh, you're already the first one here. Congratulations. Very well. Heel goed gedaan. Okay, next one. Twan. That's for you. Beautiful diploma. Heel goed gedaan. Gefeliciteerd.
Thank you.
Alsjeblieft. And I'm just checking, but I think that's were the diplomas for this time. No, okay. But I also, wait, sorry, one moment. Maybe I just want to also congratulate the whole group. Very nice project, and yeah, thanks a lot for being such nice people and students to work with. So very well done. Sorry, I'll get.